In this part, we explore data fragmentation as a means to reduce the complexity of inference in exceedingly large dimensions, and in particular, we develop a scheme called coded compressed sensing. Our starting point is unsourced random access and its compressed sensing formulation. Here y is again equal to matrix phi times a sparse vector s plus some noise, and the difficulty arises from the width of the matrix, which is 2 to the 128, or approximately that size. And the issue is that this is way too big for us to use standard compressed sensing solvers. And so we need to take actions to reduce the complexity or the width of the matrix. But luckily, for the problem we have in mind, the undersampling fraction and the sparsity levels are very small. So we have some leeway and we want to take advantage of that. Recall that the index representation is key in developing a compressed sensing interpretation to unsourced random access. The encoding process starts from the top here with a binary sequence, in this case, a sequence of all zeros followed by 1, 1. We can interpret this binary sequence as an integer, in this case A3, and then we can also develop a message index representation for this particular binary sequence. In this case, you have a 1 in the third location counting from 0, and 0s everywhere else. When the index message is folded over the codebook or the sensing matrix, you get the transmitted signal, which appears in dark blue on this slide. A key idea behind data fragmentation is to partition the original message into fragments of a reasonable size. For instance, if we start with a message of 128 bits, we can partition it into sections of 16 bits. We then have a sequence of sections that can be handled independently, and we apply indexing to each of the fragments. In this case, because we have a much smaller fragment than the original message, the compressed sensing problem that ensues will be of a reasonable size. For instance, the width of the compressed sensing matrix will be 2 raised to the 16, and we can use standard compressed sensing solvers to recover the list of fragments associated with the first slot. We can do the same for the second slot and the third slot, all the way until the last slot is recovered. There are some drawbacks. First of all, one will recognize that the output of the compressed sensing solvers will be unordered lists of fragments, as it was for the unsourced random access problem. The task of stitching the fragments together remains, and that's what we look at next. Without additional information, it is simply impossible to stitch the fragments together. So a second key idea to coded compressed sensing is the introduction of an outer code in the form of parity bits. Here, starting with the original message at the top, the next step becomes the addition of parity bits before fragmenting the message into small sections. From there, we can perform indexing and compressed sensing recovery for the multiple access problem. The stitching then happens through the outer code using standard error correcting techniques. Let's look at the encoding process from a device perspective. The device starts with an information message with W bits, and it wishes to add P parity bits to it in the form of an outer code. We will allocate the parity bits based on the order of the fragment. For instance, the first fragment has 0 parity bits, and then the second fragment will have some parity bits, the third fragment will have some as well, and towards the end we will allocate several parity bits per fragment. Once this is done, the encoded message is fragmented into small sections, and then, as usual, we have the indexing and the transmission using the compressed sensing interpretation. Except this time, we will have one message during slot 1 corresponding to the first fragment, one message in slot 2 corresponding to the second fragment, and so on. At the device, because there's only one message being transmitted, the vectors on the right are 1 sparse. These index vectors are then used to select the proper signal for the corresponding slot. The multiple access channel naturally adds the signals from all the active devices. So during slot 1, the access point will have an observation that's equal to the sum of all the signals associated with the first fragments from the active devices. Likewise, for slot 2, the observation will correspond to the sum of all the signals associated with the fragments at the second level. Similar process will happen for slot 3, 4, all the way to the last slot. A standard compressed sensing solver is then applied to the signal acquired within every slot. So within slot 1, the solver will produce a list of K fragments. In slot 2, we'll have also a list of K fragments, and so on. Now we're in a good position to explain the disambiguation process. In the original coded compressed sensing scheme, parity bits within a fragment are essentially linear random combinations of information bits contained in fragments that precede it. For instance, the parity bits in list 2 are linear combinations of the information bits in the first fragment, and parity bits for fragments in list 3 are random linear combinations of the information bits in list 1 and 2. The disambiguation process starts by selecting a root node on list 1. This node has k possible descendants, and therefore it generates k candidate paths. However, not all paths will be parity consistent. To discard some paths, what we can do is to collect the bits contained in the root fragment, compute the parity pattern that they generate, and then only return the paths with matching parity pattern under second fragment. We emphasize that the correct path will always survive pruning, provided that all of its fragments are on the output lists. The process then continues with fragments on list 3. Every candidate path has k possible descendants on this list. However, again, only some of the path will be parity consistent. To prune the tree, what we must do is look at the information bits from fragment 1 and 2, compute the corresponding parity pattern, and make sure that this parity pattern appears on the third fragment. If they don't match, this path can be immediately discarded. Otherwise, this path survives the process. In this way, we build a tree starting from a root node. At every stage, we seek to add k descendant, but only retain the ones that are parity consistent, and move forward. Hopefully, by the end of the process, only one path remains for this particular root fragment, thereby yielding an output message. A pertinent question at this stage is, where should we allocate the parity bits? To be able to answer this question, we must understand the performance of random codes a little better. We start with a W bit message and generate P parity bits using a random generator matrix G. Mathematically, we have P is equal to W times matrix G. Suppose that we pick another information sequence, say WR at random. A relevant question is, what's the probability that it produces the same parity pattern? This will happen if W times G is equal to WR times G, or through linearity, if the difference between W and WR over GF2 lies in the null space of G. The probability that this happens is equal to 1 over 2 raised to the rank of G. This is somewhat standard. The problem becomes slightly more complicated when parity bits are embedded in different fragments. Here we have a message with 4 fragments and 3 sets of parity bits. Recall that the parities within a fragment are generated based on information bits contained in the fragments that precede it. 2 randomly generated code will have the same parity patterns if the following 3 linear equations are fulfilled. This is equivalent to applying the lemma we had on the previous slide 3 times. Another way to view this is to say that 2 sequences will generate the same parity patterns if their difference over GF2 lies in the effective null space of generator matrix G. However, one of the subtleties in the analysis of the CCS outer code is that competing sequences are not generated uniformly at random. Rather, they are pieced together from the outputs of the CS solvers. For some candidate paths, This reduces the effectiveness of parity bits and it makes the analysis more complicated. Without going too much into the details, we illustrate what can go wrong through a simple example. For a path that's composed of fragments from distinct messages, the probability of this path surviving the pruning process is 1 over 2 raised to the rank of g, as expected. However, when a candidate path has fragments coming from the same message, but not all of them, the discriminating power of the parity bits is not as much. In this example, the candidate path has 3 fragments from message 1 and 1 from message 2. Because both fragments 1 and 2 are coming from the same message, the parity bits contained in section 2 will be consistent with the information bits in section 1. In fact, for this toy example, the probability that the candidate path survives pruning is 1 over 2 raised to the rank of g, where g is the degenerate matrix shown below. It has fewer non-zero blocks compared to the one on the previous slide. Trying to compute the exact probability of error for disambiguation in coded compressed sensing is difficult. The number of patterns to keep track of is related to the Bell numbers, which are known to grow very rapidly. This task essentially becomes intractable even for problems of reasonable sizes. To simplify our lives, we need an approximation. Conceptually, our proposed approximation disregards the idiosyncratic changes that occur when several fragments come from a same message. This is what caused the puncturing of the general matrix on the previous slide. Our approximation is good provided that the sections are long enough and that the number of parity bits is also large enough. This slide is supposed to convey the fact that, under this approximation, performance becomes tractable, and based on nested conditioning, it's possible to compute expressions for both computational complexity and the probability of error through disambiguation. With this characterization, we can then pose the parity allocation problem as a relaxed geometric programming optimization. This assumes the following form. We want to minimize the expected complexity, subject to a constraint on the probability of error, a prescribed total number of bits, and an integer constraint that arises from the discrete nature of bits. Altogether, this formulation can be implemented using standard convex solvers. For a simple problem with 200 active devices, 11 sections, and 15 bits per section, the optimal allocations appear in this table. The first column is the probability of error, the second column is the expected computational complexity, and the third column is the allocation of parity bits to section 2 through 11, each with a maximum of 15 parities. The specifics of these allocations are not that important. However, the character of the solution should be clear. There is a ramp-up phase where very few parity bits are being used. This promotes a growth in the number of paths. This is followed by a constant allocation where the tree girth is maintained. Finally, at the end, there is an aggressive pruning phase. When parity bits are concentrated towards the end, performance is much better, but complexity is huge. Alternatively, when parity bits are moved to earlier stages, the probability of error increases, but the complexity is greatly reduced. This highlights a natural trade-off between performance and computation in the CCS outer code. When it was first introduced, CCS was the best low-complexity URA scheme for the message lengths and the number of channel uses put forth by URA. On this figure, the x-axis is the number of active devices ranging from 25 to 300. The y-axis is the required EB over N naught in dB for a per-user probability of error of 5%. The dash curve at the bottom is the joint ML benchmark derived by URI. The red dash curve is a theoretical fourfold ALOA scheme. The top curve was the first low-complexity scheme proposed by Ordentlich and Poliensky. The blue curve is a scheme based on successive interference cancellation by Vem et al., and the yellow curve is coded compressed sensing. As we will see, many schemes have outperformed CCS since it was first introduced. Still, it's worth mentioning that data fragmentation and the CCS outer code have inspired many researchers in creating novel URA schemes. The first example of an unsourced random access scheme that leverages coded compressed sensing, is the CHIRRUP algorithm by Calderbank and Thompson. This work takes advantage of the properties of second-order Reed-Muller functions and of coded compressed sensing to create an ultra-low complexity unsourced random access scheme. The recovery process for the inner code is based on two applications of the Hadamard transform. The outer code is then used to stitch fragments together. The ultra-low complexity is achieved at the expense of sample complexity, or it requires additional channel uses. For this reason, it's difficult to compare it with the other schemes that we had on our previous figure. Still, this is a nice example of where coded compressed sensing can be used to expand an existing scheme. Another extension to data fragmentation comes in the form of enhanced coded compressed sensing. Here, a key observation is that CCS operates in a sequential manner. As such, we can take advantage of the decisions taken in the early stages of the process to inform the decoding at the later stages. Let's see how this works. The operation of the system during slot 1 is unaltered. Devices look at their first fragments to determine their own code words. They then transmit the corresponding signal, which are added over the multiple access channel, and the receiver uses a standard CS solver to recover a list of fragments. At this stage, the receiver computes parity patterns for all the fragments that were recovered during slot 1. These are all the admissible fragments. The complement of this set is the collection of all inadmissible parity patterns. Note that any column in the sensing matrix for slot 2 that's attached to an inadmissible parity patterns can readily be discarded as it can never be consistent with a fragment that's on list 1. So we can reduce the width of the sensing matrix for slot 2 before we perform the recovery for that stage. This is how we can leverage the information collected during slot 1 in performing support recovery for slot 2. Likewise, we can gather the information we've collected from slot 1 and 2 to inform the process during slot 3. The way we do this is we compute all the parity consistent paths composed of fragments on list 1 and 2. Each of the consistent paths will create a valid parity patterns for slot 3. If we gather all of these patterns and take the complement of this set, we get the inadmissible parity patterns for slot 3 based on the information produced by slot 1 and 2. Again, here we can prune the matrix for slot 3 based on inadmissible parity patterns. This reduces the complexity of the recovery task during slot 3. And this process can continue forward, identifying valid paths thus far, computing parity patterns, identifying inadmissible patterns, and pruning the matrix for the next stage. When the number of active devices is reasonably small, the pruning of the sensing matrix is quite significant. This reduces the complexity of the recovery task and improves performance. Just to get an idea, we look at the expected column reduction ratio. On the x-axis of this graph, we have the number of active devices, and on the y-axis, we have the normalized column reduction ratio. For the first slot, there is no column pruning because there is no information to take into consideration, so the line stays at 1. However, when we proceed to slot 2, 3, 4, and so on, we can see that there is significant pruning in the column. In fact, for the later slot, the pruning can become quite drastic. This explains the reduction in complexity of the system. One lesson to retain from enhanced CCS is the fact that the information from the outer code can be incorporated into the decoding of the inner code. And this is something that will come up later again. A third example where ideas from coded compressed sensing found their way into new algorithms is this application of unsourced random access to massive MIMO by Fengler and his co-authors. This setting is a significant departure from the model we've seen so far in that the access point has multiple receive antennas. This changes both the nature of the received signal as well as the character of the solution proposed by the authors. The recovery process relies on the properties of the massive MIMO system and takes the form of an iterative solution to a non-convex optimization problem. Since the signal model is quite different from what we've seen so far, it would be lengthy to describe how the signals are recovered. However, it suffices to say that the authors cleverly used the CCS outer code in their recovery mechanism. In summary, we have seen how coded compressed sensing can be used to reduce the computational complexity of support recovery tasks in very large dimensions. This algorithm is built on two notions: the data fragmentation that occurs before the indexing and the creation of a compressed sensing problem, as well as the presence of an outer code that enables message stitching. These ideas have found their way already into other unsourced random access algorithms, and they may also be valuable for people interested in support recovery in large dimensions. We'll leave you with a few pertinent references.